All right, so this video is going to serve as kind of another review of the antiderivatives that you learn about at the tail end of a Calculus 1 class. And, you know, the real reason behind the antiderivative is that it relates very heavily to integrals and what you'll learn about in a Calculus 2 or a Calculus 4 course, even when you're working a lot with those integrals. And so the idea is very straightforward, right? We're very familiar with taking something that looks like x cubed, and if we think about, just on an elementary level, right? How did we take the derivative of this in the past, right? There were really two steps. The first thing that we did was you would bring down that exponent, or what we might say a little more concisely as multiply by the exponent, right? And so just dealing very specifically with the power rule right now. And then the second thing we would do after we brought down that exponent is we would subtract, right? Subtract 1 from the exponent, okay? Subtract 1 from the exponent, right? And that would lead us to our derivative, which in this case would be 3x squared. And so this is us taking the derivative with respect to x. Remember, those d's kind of stand for change in something. So the change in something with respect to the change in x. That's how we get to 3x squared. And so what we're very interested in is going backwards, right? How do we come up with a process for undoing this? And for right now, we're just going to be tackling undoing the power rule. Okay, so undoing the power rule is what we are up to at this exact moment. And for right now, I'm not going to use any symbols per se. You might see this symbol right here that kind of some people associate with the antiderivative. I'm not going to use that symbol. I'm just going to simply say out loud, if we want to do the antiderivative, if we want to undo these steps, you kind of have to think about it like putting on a pair of shoes, right? Like if you put on your socks and then you put on your shoes, in order to undo that, you need to take off your shoes first and then take off your socks. So the first thing that we're going to do to kind of undo this process is we're going to do the opposite of this last step here. So instead of subtracting 1 from the exponent, we are going to add 1 to the exponent, okay? So that's the very first thing that we're going to do. And then the second step, right, what did we do with that before? Well, before we would multiply by, the exponents. So to undo that, we are going to divide by the new exponent, we'll say. Divide by the new exponent that we just got, which should kind of make sense, right? If I do this process and I add 1 to that exponent, I kind of get to 3x cubed. And then if I divide by that new exponent, right? So I have 3x cubed and I divide by that exponent of 3, I'm just going to get back to x cubed. And so this two-step process is how we undo the power rule. So very useful for polynomial functions. And just to kind of drive home the point, if I have y is equal to let's say x raised to the 3/2 power, and I want you to basically, let's say that this is a derivative, maybe I'll use that notation, that y prime is equal to x to the 3/2, right? Then in order to undo this, right, y is going to equal, well, the steps are that we add 1 to the exponent, so we're going to have x raised to the 5/2, and then we're going to divide by that new exponent, so divide by 5/2. And at this point, we need to remember that dividing by 5/2 is the same thing as multiplying by 2/5. So we get something like this, and that'll do it. Okay, we can say that is an antiderivative of x to the 3/2. Now, one thing I want to point out really quick is this kind of interesting scenario or situation that we may find ourselves in, which is, what if I were to ask you, if I give you y is equal to x cubed plus 7, what would you say is the derivative, right? Well, y prime here would be 3x squared, and then the derivative of 7, because it's a constant, is just 0, so we just get 3x squared. And likewise, if I were to ask you, what if I give you y is equal to x cubed minus 10, and I said, well, what's the derivative? You would say, well, the derivative is still 3x squared. And so it kind of seems like we're missing a little something, right? That maybe in general, if I were to give you, an equation, y is equal to x cubed plus really any constant c, which I'll denote like this. I'll say c can be any real number. So this notation here, that really means is like kind of is in, and then this kind of double bold-faced R here is the set of all real numbers. Okay, or you can kind of think about that as, you could also write it as C is in the interval from negative infinity to infinity. Just some fancy notation that means C could be any real number. But the point is that if I give you this function, the derivative of it is still going to be 3x squared. And so in this process that we were doing before, where we were saying, okay, we know how to take a derivative, how do you go backwards? And we got to the point x cubed. Technically, the more general answer is that this function that we came from, right? If we were to start with 3x squared and say go backwards, right? Go back. What original function did you come from? X cubed could be an answer. X cubed plus 7 could be an answer. X cubed minus 10 could be an answer. And so more generally what we say is that the answer is not just x cubed. We would say that the answer is x cubed plus c. And so what does this look like in action? So for instance, if I were to say, give you that the derivative of something was equal to 2x to the fifth, and I want you to, find the general antiderivative. Okay, general antiderivative. So what we're looking for is to get some equation y is equal to something, and we're going to follow our own rules, which is we're going to add 1 to this exponent, 2x to the 6th, divide by that new exponent. But we know that technically speaking, there could also, in theory, have been any constant added to this, right? Like if I take the derivative of this, right, if we wanted to check our answer going this way, the derivative of this, right, we could bring down the exponent. The 6 is going to cancel with the 6. We'd subtract 1 from the exponent. We get 2x to the fifth, and the derivative of the constant is just 0. So the general antiderivative here would be 2x to the 6 over 6 plus c, and we could trim that down to be x to the 6 over 3 plus c. I'd say this is a more common way to write this answer. So that's just the way that we go about undoing the power rule. And as you learn about antiderivatives and really the purpose of an integral calculus class, the purpose is we want to learn how to do more than just the easy antiderivatives. Okay, and that's kind of like what we study in this class. But since this video is about the elementary ones, let me just kind of recap a few of the common ones. So for example, if you were given that the derivative looks like 1 over x, we need to have, a familiarity with recognizing, okay, well, if this is the derivative, what function did it come from, right? Another way of thinking about that is, what function has a derivative, right? When we go down this way and we take the derivative, what function has a derivative of 1 over x? And this is where you need to be really familiar with your derivatives, because hopefully we remember that this is the natural log of x, and then you think, okay, plus c, right? Now there's actually a kind of another caveat that kind of comes up with this. So again, it's very natural to think that the antiderivative of 1 over x is the natural log of x plus c. That is 99% of the way there. But one little funny nuance that kind of happens here is the fact that if I tell you this is the derivative, well, x could be any value, right? X could be positive numbers, but even worse, something we have to be careful of is that technically in this function, x could take on negative numbers. But the problem with that is that what do we know about the natural log? Well, the natural log is not defined for values of x that are equal to 0 or less than 0. It's not defined for negative numbers. It's not defined for 0. So the natural log of x only works, right, or only has answers for x greater than 0. And so the way that we actually do this is we say that, if y prime is equal to 1 over x, then the antiderivative is, we would say, is the natural log. Well, what's the only way that I can make sure that I'm always going to get positive numbers in there is we say the antiderivative is the natural log of the absolute value of x plus c. That's what we would say here. Kind of by doing this, it kind of does exactly what we expect, right? The derivative of the natural log is 1 over x. The derivative of c is 0. So it does what we want it to do, but we kind of save our bacon by throwing in that absolute value sign. So this one's kind of a little bit strange, but the more we do it and the more we start getting familiar with kind of considering domains, that we really want to make sure that if we're doing derivatives and we're doing antiderivatives, we want everything to work. We don't want things to break down and fall apart for us. This will kind of be a little bit more comfortable as we go. Let's see, how about another one? What if I give you that the derivative is e to the x? All right, gosh, do I happen to know what the antiderivative of e to the x is? Well, there's only one function whose derivative is e to the x, and that function is itself e to the x plus c, right? We're going to add this plus c, and that kind of covers our bacon. Again, making sure, right, we can always check our answer, right? How do you check your answer? You just take the derivative and make sure that, that things kind of line up. The last one that we're going to kind of need to be able to work with are our trig functions. So, for instance, if I tell you that the derivative is equal to secant of x times tangent of x, and I'm asking you what is the antiderivative, right? What is the function from which this comes? You need to be able to know that, to think backwards, say, okay, the derivative of what is equal to secant tangent? And it turns out that the derivative of secant of x is equal to secant tangent. So the antiderivative of secant tangent is just going to be secant plus c, right? Not too bad. Let's see, what if I asked you, right, what if I give you that the derivative is equal to, let's see, negative sine of x? What is the antiderivative? Well, what function has a derivative of negative sine of x? That's going to be cosine of x plus some constant c, right? So if you've kind of forgotten some of the easier derivatives to know or to work with, you can go back to the derivative video that's posted also in this course and kind of just brush up on those derivatives and make sure you really have them under your belt, because you need to be able to reword these sorts of equations in your head, these sorts of questions, that when you're being asked the antiderivative, you need to be saying, okay, what function has the derivative of blah thing? And for these ones, which I would say are going to be our level 1 kind of starting points, you really want to have them in your back pocket. That way, when we start doing harder examples, you're not even really needing to think about it. Now, as I mentioned, these are the easy examples, and this is kind of where this video ends. But, you can imagine that as I start to give you more interesting derivatives, like what if I ask you, what if I give you something like this? Right? All of a sudden, now it's not so easy to be like, oh, the antiderivative is blah function, right? Because it's a lot harder to answer the question, the derivative of what is equal to 2x e to the 2x or something like that. And so that is pretty much what the entirety of this class is going to focus on, is kind of how to work with these sorts of questions, and which ones can we answer and which ones can't we answer. And that's where we're going to be going. So hopefully this video was good. Again, a little bit of jogging the memory of those antiderivatives that we learned about in Calc 1. And at this point, you should be ready to start the class.